Okay. Hi, folks. Welcome back, and welcome back to MLDublin's first ever remote meetup. I hope everyone's been keeping very safe and well since our last meetup in February, which seems like an awful long time ago now. We're hoping to make these a bit more of a regular occurrence. We're putting out an open invitation to any of our members of the community. If they have any topics that they would like to suggest, or if anyone would like to volunteer to speak, please get in contact with any of the hosts on the meetup page afterwards. That would be really very much appreciated. So just to fill you in on some of the activities that we've been doing in Adapt since we all last saw each other. So apart from the obvious disruption of the COVID pandemic, we've actually had quite a lot of activities, various research and commercial activities going on. So we had one of our spin-out companies, Iconic Translations, was recently acquired in a multi-million euro deal by RWS Holdings. It's a translations company based out of the DCU side of the Adapt Centre. We also had a large response to the SFI COVID rapid response funding call, and one of our colleagues, Professor Orla Hardiman, had one of her proposals accepted. So she will be doing a COVID response project around telehealth to support vulnerable groups during the pandemic. And we've also recently begun a collaborative applied research project with a data cloud company called Informatica, looking at ways to better automate their data management systems. So I'll hand over now to Alex O'Connor, one of our speakers from Autodesk.
Thanks, Claire. Can everyone hear me okay? Autodesk, we're very happy to participate in this event. I actually was involved in the MLDublin projects back when I was in Ireland, so it's a nice opportunity for me to take advantage of the unusual circumstances to broadcast back home. So it's great to see hopefully some familiar faces along the way. Just to briefly introduce Autodesk, we are a leading software developer in a wide variety of areas, but especially in construction, manufacturing, media and entertainment, and anything to do with creation. So we enable our customers to build products, build content, really build anything they have an idea for. So anytime you see a major construction project, a high performance vehicle, or a 3D animation, is a good chance that one of our products has been involved and one of our users has been involved. So we have millions of users globally. We have who are working professionals who are highly expert in their tasks, and that makes it a very exciting place to work. And if you are interested, we are hiring. We have offices in the US, in Europe, in Asia. We have numerous offices, and many of them are hiring for data-related roles. So please do go to the site, have a look, and see if there's a job that might suit you, and feel free to apply. If you have any questions about a particular role, to get in touch with us, and we can clarify or make a referral or those sorts of things. So with that in mind, I'll hand back to Claire for the first talk. Thank you.
Hey, Claire, are you going to introduce the first speaker?
Yes. Yeah, sorry, I was on mute. Sorry. So our first speaker is Hui Li, who is a colleague of Alex's in Autodesk, and she will be speaking about reinforcement learning for robot assembly of timber joints.
Thanks, Claire. Everyone can hear me okay? Okay, so let's share this. All right. Yeah, so today I'll talk about a project we did very recently, sim-to-real reinforcement learning for robotic assembly of timber joints. My name is Hui Li. I'm a principal research scientist at Autodesk Research. And more specifically, the Autodesk Robotics Lab, located at Pier 9 in San Francisco. Here's a picture of the lab. We have industrial robots, like those giant black KUKA robots in the middle, and also smaller robots, the URs and a Panda robot that are more collaborative and safer. So we work on a variety of projects, a lot of involving reinforcement learning, so learning to control the robots, intuitive robot interfaces, and like a variety of projects going on. So this project is a collaboration project between the Autodesk Robotics Lab and the Grammatic Kohler research at ETH Zurich. So automated assembly using robots has been commonplace in manufacturing, but in architectural construction, it's still in its infancy. One of the main reasons is that buildings are usually bespoke. So designing and developing the automation system and process is very time consuming and requires a lot of investment. So there has been some progress in automation, construction automation in areas like brick building, brick layering, or the timber frame manufacturing, or mesh molding. But these systems all require very sort of standardized modules, and also cannot adapt to any errors or misalignment during the process. So our vision is to actually build a free-form timber architectural scale structure using robots. And we want the robots to be able to react to various situations, errors, misalignment, without humans having to interrupt and pre-program the process. So this structure is basically composed of a lot of different types of tight-fitting timber joints. And so there are two main challenges in this. One is the joints are very tight-fitting, so it requires quite a bit of force to insert the timber members. And two, because of the material and the structure, errors and misalignment will be unavoidable. So in the project, we just focused on this one sort of part of the whole process, which is when the timber members are in very close vicinity of each other. So during that time, contact force is present. And so the rest of the robot motion, like from picking up the piece to moving it over to the structure. So this is like coarser motion, and that can be handled by a motion planner. So here we're not considering that part of the problem, only looking at this when the timber members are close to each other and there's force feedback. Here's just some close-up pictures of the timber joints. They're very tight joints, 1 millimeter tolerance. So the research question we ask in this case is, can the robot learn how to assemble timber joints based on real-time force-torque feedback? More specifically, can the robot controller, can we learn this robot controller that assembles tight-fitting timber joints? So on the left side is a CAD model of our setup. On the very top, the red cylinder is the force torque sensor mounted right between the robot and the gripper. So beneath the force torque sensor is a gripper, and it's gripping a top timber member, and on the bottom there is a static member. So now we want to learn this robot controller. The input to the controller is two things. One is a force torque feedback from that force torque sensor, and two is the member pose of the top member that's being moved by the robot. It has position and orientation. And the output of this robot controller is velocity command, basically in Cartesian space where we command the robot to go. And here is a side-by-side comparison between our setup in simulation and our setup in the real world. So then later we'll learn basically the approaches. We want to learn everything in simulation, and we transfer that into to run it on the real robot. So the approach, we'll call it sim-to-real reinforcement learning. It's composed of a few elements. So one, we build upon Apex DPG. This algorithm, it's basically a distributed version of deep deterministic policy gradient reinforcement learning algorithm. I'll describe each later in more detail. And so we add one human demonstration to guide training. And to go from simulation to the real world, we use two things. One is domain randomization, and the other is system characterization. So next, I will explain them one by one. Just a bit about reinforcement learning for folks who are not familiar. Reinforcement learning solves the set of control problems where there's an agent and it's interacting with an environment. The agent, based on its current state and the reward, it's basically it outputs an action to interact with the environment, and the environment outputs the next state and the next reward. So the goal of our control is to how can we maximize the total expected reward. So two things are important here. One is basically what actions do we perform, right? So what actions can the robot do given the states? And also, how good are these actions? So how do we value these actions? So there are two functions here. One is a policy. It's a behavior function selecting actions given states. The other is a value function, QPI here. Basically, it's the expected total reward given the state and the action under this policy pi. So more specifically for continuous control problems, DDPG is a pretty popular algorithm. It stands for deep deterministic policy gradient. Deep because here those functions I just mentioned now are represented by neural networks. And so here we have an actor network that represents the policy pi. And we also have a critic network that represents the value function, Q. And there's a third ingredient, which is experience replay. It basically stores transitions. So one transition is the current state, current action, the current reward, and the next state. So we basically formulate each the experience of, say, putting together a timber joint as a whole sequence of transitions. Store these transitions in the experience replay buffer, and then we can sample them according to some rules, maybe just random sampling. This way we can remove the data correlation during training. And last ingredient is there's basically two target networks. Each is a clone of the actor and a critic network. This way, the target networks update periodically. This way, we can avoid oscillations. And an extension to DDPG is Apex DDPG, which basically is the distributed version. And so it has, we can run multiple actor networks in parallel, asynchronously. And so each actor network interacts with an environment instance. And here the environment is a simulation environment. And there's one learner network that basically samples the experiences from the replay buffer and updates the priorities and parameters in the neural network. And there's also, so like the way the experience or the transitions are ordered in the replay buffer is called prioritized experience replay. It prioritizes the unexpected transitions, so a bias towards the transitions that are unexpected and give us more information. So on top of the Apex DDPG framework, we add a human demonstration. And here, so in simulation, we control the robot by either a joystick or a space mouse. And we just record one task iteration. So we have the human demonstrator complete the task, and then for one episode. And each transition it's in the same form: current state, current action, current word, and the next state. We store this episode in the replay buffer as well, and that gets sampled by the learner network. So here's just a quick video on how we do it. It's a PyBullet simulation environment. We're using the human demonstrator completes the task, and that is stored in the replay buffer. Here's just an example of the training process in simulation. As you can see, as the iteration number increases, the reward starts to converge and success rate increase as well, until when it gets to a little over 100 iterations of training, the training is successful. So okay, so now say we have a successfully trained model in simulation. How do we actually use this? How do we make sure that works in the real world on the real robots with real timber pieces? So one technique we use is domain randomization. It's a simple idea. So we randomize the simulator to expose the model to a wide range of environments at training time. And if there's enough variance in simulation, models trained in simulation will generalize to the real world without any additional training. So you can pretty much randomize anything in simulation. It can be observation states, like in our case, member poses or force torque readings, or actions. In our case, velocity commands, or timing. Maybe there can be, like the actual controller of the robot, there can be a delay, and the control delay. And physical parameters, friction or the mass of each robot link, or the objects, and the visual appearances. Here's an example. In this work done by OpenAI, basically the goal is to train an object detector on rendered images. And so in training time, they randomize a lot of things, such as camera positions, lighting conditions, object positions, and texture. And so all these variations in training and in test time, they use the real world image taken by the camera mounted on the robot. So this technique works generally pretty well, but the downside is training takes a lot longer, and the basically more randomization you have, the longer it takes. So through experimentation, we found it's effective to randomize these two things. One is the force torque observations, And basically, the force torque feedback we get in simulation is very clean, but in the real world, there's a lot of noise. And as well as the friction parameters in the simulation engine. So we found randomizing these two things are very effective without making the training a lot longer. So basically to bridge the gap between simulation and the real world, we go from two directions. One is in simulation, we use domain randomization as effectively as we can, so that the real world is an instance in this distribution. The other direction is we want to learn as much as we can the real system, so we characterize the real system to basically meet in the middle so that we can most effectively close the gap. So the workspace is at ETH Zurich at the GKR. They have multiple ABB IRB 4600 robots hanging upside down on gantries in their lab. And so we did a study on the whole control profile, and there is a control delay to the system. So once we characterize that, and we can match the control rate in simulation to the real system, and that's a lot more effective than randomization. So I'll now show you some experiments we did and results. Just briefly, here's our software hardware interface architecture. On the left side, we have an external computer that runs the reinforcement learning policy, the trained policy there, and the other is the ROS interface. And in between, so the policy will output actions, the velocity command to the robot. And basically that talks to the ROS interface, and in turn, that gives the velocity commands to the real robot controller in the robot work cell. And the reinforcement learning policy also takes observations from the ROS interface that is pose and also force torque, and which also interacts with the real force torque sensor on the hardware side. So first experiment is to see just the same environment, the same task. After we train the model successfully in simulation, can we run it in the real world successfully? Okay, good, it's running. Yeah, so here it shows it's very smooth at 100% success rate on the real robot with the timber pieces. So next we think, well, so the idea is for the robot controller to be able to adapt to errors and small misalignment. Can we do it? Oh, hold on. Just before we go there, just to show you a comparison between simulation and the real data. So this is the a pose of the timber member. On top is the position, X, Y, Z, and then bottom is orientation and quaternion. One big thing you can notice is that there's a lot more noise in the real world than in simulation. And you can see as the colored bands there. So next set of experiments we did is basically when we have some offset. So here is the linear offset of 2 millimeters on the X and the Y position. Can the same controller, can the same trained model perform and adapt to the offset? And it did 100% success rate as well. So next one, we also added orientation offset to see, and also on the Z linear offset to see whether it can adapt well. It's also successful. And So besides sort of testing on different offsets from the original model, we also want to know whether this trained model can adapt to different joint angles, different types of joints successfully. Because putting together a freeform structure, I'm sure not every joint is of the same 90-degree angle. So we say, well, let's try 75-degree angle single lap joint on the same trained model. And it also worked successfully. And so basically the idea is to let's keep pushing and see where this model fail. So we increase the difference to 60 degrees angle, and then all the way to 45-degree angle, and that's when we failed. But this is not surprising. I think it's a little unreasonable for us to test a model trained on 90-degree joint on a 45-degree, but at least we know sort of where the range of adaptation is. And we also looked into different types of joints. Maybe now we have double lap joints instead of a single one. Here, the lever, so because the force torque sensor is right in the middle, the effects will be different. So this is a new model trained in simulation that's successful, and we can also we can also successfully transfer that onto the real system. Okay. So here's conclusion. This is, to our knowledge, the first demonstration of reinforcement learning in architectural construction with industrial robots. And we show models trained in simulation can perform well in reality and also adapt to misalignment and shape variations. We think this is a small but first step towards fully automated timber construction. Some future work includes we want to test more sort of joint types and geometries and extend it to a partially observable environments for POM-DPs where only force torque observation is available, no pose. And also adding constraints in the training, for example, to limit allowed force torque. So that's my presentation. Thank you. And also, Robotics Lab is hiring software engineer positions for machine learning and simulation. Please take a look on the job site. With that, I'll stop sharing. Thank you.
That was great, Wei.
Yeah, thank you, Wei.
Thank you.
Great, thanks, Wei. Yeah, if there's any questions, people can just put them in the chat on the YouTube stream.
So I was going to ask one actually, Wei. Striking that balance between your sort of your synthetic data in your domain randomization piece and real world observations, how did you get the balance right?
Trial and error.
Yeah.
Yeah, basically, we cannot afford to randomize everything. We don't have, the huge AWS training farms to do all that or time. So I have to basically, there are a lot of intuition that went in as well. It's like basically force torque feedback. It's so clean in simulation, but it's just very different from the real world. And And honestly, like the control delay of the real robot system, we did not think it would be an issue, but it turned out to be a very significant factor. But that's basically from experimentation. So yeah, combination of things.
Cool.
Very cool.
Great. Thanks, Wei. So next up is Alex Carlson, who's also from Autodesk. So I'll just hand over to you, Alex, so that you take the lead there.
All right, excellent. Well, Wei mentioned not having a huge AWS training farm to be able to just try everything. So maybe what I'm about to go over might help with that. So that's actually an excellent lead. Let me just go ahead and share my screen. Entire screen. Let me pick the correct one. All right. All right, can everyone see my screen? Excellent. All right, so, my name is Alexander Carlson. I'm a machine learning engineer at Autodesk on the Fusion machine learning team. I work on our machine learning pipelines on cloud and production infrastructure and on data sets for a lot of our machine learning projects. Since we are Autodesk, we have a lot of very unique data, as you might imagine, and data types that are not very well explored in the machine learning space, but it is very important data. So we have a lot of 3D data and simulation data and architectural data. So in addition to machine learning, we also get to explore things about physics and 3D geometry. So around October of last year, we were approached by AWS to test out their new SageMaker debugger and run a proof of concept experiment with it. We've been working with them earlier in the year, getting our new ML feature out to production. That feature was visual similarity search in generative design software within Autodesk Fusion 360. So I spoke about the SageMaker debugger in December at one of the AI ML classes at AWS reInvent, along with the release of the SageMaker debugger. We're going to be going over the ML feature that we released. We're going to go over the experiment we ran with the SageMaker debugger, and we're going to go over a bit about how you can implement the SageMaker debugger yourself. So first, we'll start with generative design. So in a traditional manufacturing tool, you model a part yourself with a goal in mind, and then you test it, and you hope it will withstand the forces that you designed it to withstand, but you don't really know until you test it. In generative design, you start with an idea by giving the required connecting pieces and a set of forces to the program, and it will generate many outcomes for you that all satisfy your design requirements. I'm just gonna do a quick little demo of how the UI on this looks. So you start with your starting shapes. I just used a couple of boxes for an example. You slap a constraint on there, and a constraint is just the equivalent of bolting something to the wall or to a floor. You can then just add a load. Oh, that is so that is a constraint. We're just gonna put a load on here now. We're gonna give this we'll call this 5,000 newtons. And then if I were to start solving this, it would do a large parallel solve of the forces there. But we're just going to use the previewer to get the basic idea. Previewer is actually something I also worked on. So what it'll do is it'll start with a large convex hole between the two shapes that will be able to withstand the forces that you applied. And it will gradually advect away the material until you've got something that's highly optimized. And this previewer only does a few iterations, but the real one can do more than 100. So we'll just go ahead and stop that there. I will bring up. This is something you can get if you actually let that thing run to completion. You set up your problems properly. So something cool we did with generative design. Autodesk has been collaborating with NASA's Jet Propulsion Lab on a project to design a lander to search further out into the universe for signs of life on other planets. Now, spacecraft are some of the highest performing and best engineered things that humans have ever designed. But with little life found on Mars, we now need them to travel even further. So this concept lander aims to travel 10 times the distance of Mars to the moons of Jupiter and Saturn, which even at their closest orbit is still over 580 million kilometers away, or 350 million miles for the non-metric audience listening. So yeah, this isn't even really just a concept. This is something we actually built in full scale using 3D metal printing and quite a few interesting additive techniques. So this is what you can get from generative design. So this single setup produced 48 different outcomes. The most highly optimized results are the ones displayed in the Explore user interface, where users explore the outcomes of their generative design solve. However, you aren't limited to only the most optimized solutions. Each one of those 48 outcomes also has every iteration of the design optimization process recorded, which brings the total number of results into the hundreds from a single solve. Many customers will choose one of the intermediate iterations because it's easier to manufacture, the aesthetics are appealing, or because they get a higher factor of safety that they didn't realize was possible. If you specify a minimum safety factor of 5 and an optimization goal to minimize mass, generative design will continue to optimize until it reaches the lightest possible part with a safety factor of 5 using your chosen material and manufacturing method. This is verified automatically with multiple simulations at every step. However, you might notice that one of the intermediate iterations is only 15% heavier than the final outcome, but offers a safety factor of 10 instead of a safety factor of 5. That would have been an entirely different product development and engineering cycle using traditional methods, but generative design does this for you. So this is what it might look like were you to try to look at every outcome of a generative design solve at once. We call this generative overwhelm. Now, when presented with hundreds of outcomes, you might be able to imagine that it could become a little bit difficult to find the perfect part, because every result produced will be optimized and every result will meet your design requirements, but you want to find the best one to send to the manufacturing floor. So we developed a solution, Project Kepler, which is visual similarity grouping for generative design. Project Kepler enables an option within the generative design explore space to group your results in the way that a human would group them by visual similarity. As you can see in this example, there are clear groupings between the brackets produced here. We might call these groups minimalist, latticed, and thin beams. So we participated in a preview of the SageMaker debugger to see how it could help us with Project Kepler and our other machine learning models, with rules for monitoring training jobs and the ability to visualize the internal structure of our model as it is training. For our parameter sweep using SageMaker debugger, we were able to kick off 10 training jobs at once instead of the usual 1, which we would run sequentially before, which would eat up the time and compute cost of the jobs that produce suboptimal results. We were able to do this with no change to our model code, and for the analysis part, it required a very little change to the model code. So here's an overview of the benefits we experienced, and I'll go into more detail in these on the next slides. There are 2 main things that the SageMaker debugger enables that we found most valuable. Number 1 is training in parallel with SageMaker debugger rules attached to multiple jobs, which massively reduces the calendar time and compute cost compared to running jobs in sequence and then comparing the results of the jobs after they've run to completion. Next is the ability to gain insight into the internal behavior of our model as it's training by attaching debugger hooks to the training process. This allowed us to visualize the weight distributions and performance of our gradients and layer outputs, and led us to make model changes that ultimately reduced the number of convolutions by 33%, reduced the model size by 42%, and increased the embedding quality produced from our autoencoder. By attaching rules to the execution of our training jobs, we were able to start many jobs at once and then terminate all but the ones showing the most promise. The loss not decreasing rule allows you to trigger an alert whenever a job stops reaching a lower loss, or the decrease in loss is not greater than a given percentage that you specify. This is all completely configurable. There are many rules to choose from, such as detection of vanishing gradients and exploding tensors. And if none of those work for you, you can create your own rules and have them run alongside your primary training job. And you would just configure that so that when the rule is tripped, you can automatically kill that job. So you can basically just start them all at once and then just terminate the ones that aren't great. This is how you normally do machine learning on SageMaker. You do, one job at a time. You might manually look at something and then stop it yourself, which is fine. But with the SageMaker debugger, you set it up in your training notebook. You launch every possible job that you think might be good at once, and then you automatically terminate the ones that are not the best. And then you just take the few that survive that termination process and compare those at the end. So this is a SageMaker TensorFlow estimator. And as I said before, this does not require you to make any changes to your model code. You just specify the rule here, and then you create the estimator and submit the training job. You can configure it to automatically cancel the jobs that trip the rule. So aside from the creation of rules that allow us to execute parameter sweeps in parallel without having to worry about the cost of allowing all the jobs to run to completion, SageMaker Debugger also allowed us to analyze our model. Yeah, this is just some of the analysis output, and here's some of the code that you would use to start that analysis. So yeah, this is some of the insights we found from our model. We had a L2 loss function that converged too quickly and was producing blurry results because our gradients got really, really small. And we didn't really know this for several months until we actually took a look at this and found that our gradients were getting really, really close to 0. And we were able to get rid of some of the layers. That was also quite good. So in addition to better overall performance and faster training made possible by the insights we obtained from using the SageMaker debugger to visualize the model, the reduction in convolutions also decreased the overall size of our model from 290 megabytes to 170 megabytes. This makes deployment much easier and reduces the required memory of machines used to run the inference. Additionally, with the model trained on SageMaker, we can easily launch compilation jobs that target any valid AWS NL endpoint. And that's about the end of that. We very recently released the improved version of this model to production. So if you go and try generative design, you will get the results of that. They're actually quite good. Yeah, there we go. All right.
Great job.
Cool.
Thanks very much, Alex. Are there any questions from YouTube, or if you just put your questions in the chat channel?
Actually, there was a question for Hui from earlier. How much is the real robots control system different from simulations? And then actually Sumia has asked one here for Alex. Thanks, Alex, for the lovely presentation. Can you tell us a bit more about the framework or algorithms behind the visual similarity clustering in Project Kepler?
Alice, you should probably go ahead just right after your talk.
Alex looks like he's frozen to me. Maybe it's just me, is it? Oh no, he's moving. Alex, did you get that question?
Yes. So we use a multi-view convolutional neural network for that, and it's basically multi-view convolutional neural network autoencoder. And what we do is we take a whole bunch of snapshots of the final outcome, and we append those together in order to create an input inference image. And that gets sliced up into 20 views, input into the into the autoencoder. We try to reconstruct that at the end, and we take the bottleneck layer and use that to produce embeddings. And that the clustering in the middle there is how we produce the visual similarity groups.
I can just answer quickly the question.
Sure.
Yeah, so in theory, the controls are the same, right? In simulation versus the real world, we're just controlled by the velocity at the end effector, at the tip of the robot. But in reality, there's in simulation, it's just it's very clean. You just set it there. But in the real world, there's the ROS interface. There's the communication layer. There is the actual robot controller that's doing it. So in reality, there's many layers that adding the delay and to the real system. So yeah.
Great. Thanks, Alex. So our next speaker is Alex O'Connor, who will be doing an introductory talk on transformers. So I'll hand over to you now, Alex.
Great, thank you very much. So for everyone else, this work I'm going to present is more about the application of a kind of widely available open source library that we found useful in our work rather than original machine learning research that we've done, but I think hopefully it'll be useful to some organizations because we found it to be a widespread ask. So as I mentioned before, Autodesk has this mission to support creative professionals in a wide variety of industries. That has a really number of significant impacts for us, one of which is that we need to be able to support highly expert users in their requirements. So our users are people like senior architects, senior engineers, senior designers, other machine learning professionals, other people who are themselves organizing to create highly automated or highly dynamic workflows and processes. So that means that part of our support organization has to be able to understand those sorts of problems. That creates this challenge for us that we have a customer support environment that ranges from the simplest possible questions, such as how do I find the correct download for the version of Fusion 360 that has all the exciting stuff that Alexander talked about, all the way up to the debugging of complex CFD flows in the design of a high performance vehicle. And you know, in being able to understand both of those things or being able to handle both of those sets of questions, there is this challenge that we have ample high-speed return for customer support for simple questions, but complex questions require expertise and have a long turnaround. So from our perspective, one of the ways that we address this problem is that we need to think about the fact that we have a situation where most of our communication comes in a written form. Increasingly, we have chat-based support, but we also use an awful lot of email and text-based support. And a typical NLP pipeline for any organization probably looks something like this. You have some metadata that surrounds your case, which identifies the customer by name or by an ID, and then they state their problem. And it's a set of symptoms, often with a task that they want to achieve. And this is the classic NLP challenge. I have a set of things that I need to look at. I need to extract the body of the text from the surrounding templating. I need to be able to find mentions of particular products and versions. I need to be able to obfuscate certain codes if I want to, or be able to detect those certain codes. And I have to deal with the variance in language that occurs because our customers and every human has some error or some challenge in what they do. And indeed, we often have the situation that this includes changing support languages, changing other things. So people may not be writing in their native language, or they may not be writing in the most familiar technical terms. And so in trying to address this problem, there's a kind of three things you have to think about. One is how much data do you have to learn from? The second thing is what is the specific task that you want to be able to achieve? And the third thing is how do you achieve those things in a rapid fashion so that you don't spend more time training your model than you do actually using it? Most recently in natural language processing, the interest that's emerged has been around this concept of a transformer. So there was a paper about 4 years ago called Attention is All You Need. And in that paper, they introduced this concept of a transformer, which is where you train a very large language model on a general set of objectives. You use that set of objectives to help you in all the other things that you want to do. So if you recall, those of you who are long-term members of this organization may remember the first talk I gave was about word-to-vec vectors and pre-trained language models back then. This is the evolution of that original talk now towards a much more dynamic, much more capable set of features. But along the way, a lot of the same lessons have been learned, which is that we have this ability to transform linguistic statements, sets of words, sets of tokens into a space that we can manipulate mathematically. And that's a really powerful thing because it allows us to perform all sorts of tasks. Transformers are interesting because they have become very widespread in their use very quickly. So as technology has evolved, as the availability of the open source tools and models have become there, it's the path from the lab, as it were, to the street has really shortened an extraordinary degree. Organizations around the world are already deploying transformers in production for a wide variety of solutions. They're able to evolve those very quickly and all along the way get extremely high performance from what they do. So if you have a task such as text classification, language generation, translation, you are very likely to gain benefit from using a transformer type architecture along the way. And as you do so, you are able to do it with less data of your own sort. So the intuition for a transformer, and I won't go into the kind of full theoretical details simply because of time, but is to think about this as a multi-headed self-attention, which is to say that we have multiple simultaneous readings of the sequence of the text, and along the way we look at each peer, each neighbor along the sentence in both directions, and use that to help us decide what the weight of each particular word is in the sentence. So what's the importance of one particular word with relation to their relationship of all the other words. So now all of our birds are watching each other, and we have multiple sets of flocks of kind of weightings around what the different sentence meanings are. This has a lot of power to it because what's interesting is that when you think about it, language is often a kind of a serialization of a thought. So you need often to read to the end of a sentence to be able to understand all the things that happened before. And you need to be able to use all of the information from all of the words to be able to understand the whole concept of the sentence. And earlier models took a kind of a linear direction or single directional view, or struggled to kind of understand that longer range relationship between the models. And previously we had been using recurrent neural networks. We've been using gate models for this, and I think the insight here was that actually the attention, that ability to look across multiple different steps at once, turned out to be the most powerful part of it. So these models are huge. The smallest models are in the 500,000 parameter and in the 500 megabytes kind of size. The largest ones are gigabytes in size, and we can talk a little bit about them in a minute. So what do we use a transformer for? Well, the interesting thing about transformers, as I said, you start with this baseline model that you train on a set of objectives, and then you can turn it towards specific tasks. The most kind of fundamental task is the idea of language modeling, which is the question of looking at the probabilities of different tokens in a sequence. So you can use it to guess individual words, guess the next word, guess a missing word from a sentence. A lot of people use it for text classification. So sequence classification is where you take a whole chunk of text and you say, what category does this text fit into? The most common example of this is sentiment analysis or review classification, but actually this is one of the ones that is most industrially useful because it's often the opportunity to change or reroute a piece of text along the way. Increasing the resolution, you can look at token classification, which is the opportunity to look at individual words in a sentence and ask for their role. So that's where we might be able to discover product mentions. That's where we might be able to discover specific specific descriptive terms or other individual pieces of or roles in the text. So named entity recognition and all those sorts of things. You can also zoom back out then, and you can ask it multiple choice questions. You can even ask it question answering environments. And there's some very nice demos where you supply a question and then a block of text, and the model will be able to reformulate an answer for you from that block of text, as as in the sense of the context. So you can think of this as a superpowered search for a web page or a superpowered search for sequences of text. And that's being extensively used in snippet extraction, in display, and in improvement. The nice thing is all of these things are available as we go. Probably most famous of the transformer tasks is the text generation task. So the OpenAI group have had enormous attention for their work, excuse the pun, on things like the GPT-2 model that they originally produced, and more recently the GPT-3 model, both of which allow you to generate new text from a limited context. So you can give it a starting sentence and it will continue your sentence for you. And I think the potential for that is enormous, because there's all sorts of opportunities to use that information to automate or make more textual interfaces, which are now very visual. Translation is an immensely important topic. I don't think I'd be allowed on an adapt presentation without mentioning how important it is, but additionally, translation models, because of this ability to look backwards and forwards, to look along the sentence, has the power to help a lot with language to language. Summarization is another one that shortening and abstractive summarization is especially appealing. This ability to not just find the pieces of the sentence that you want, but to actually create a summary the way a human might is a very attractive application and very relevant in a huge number of areas. Finally, we have two things that are more back in the laboratory. One is distillation, which is the idea of how do we make models smaller, how do we make them faster, and then there's a whole field of BERTology, which is the fact that we have this multi-layered, multi-headed, massive model is an opportunity for us to then inspect what it's trying to learn, what weights it's trying to learn, what things it's trying to understand from inside it, with the opportunity to understand whether or not things are happening in there that are themselves interesting. So there's been work, for example, to understand how different layers in BERT begin to reproduce the classical NLP pipeline, or how one particular region of the network becomes responsible for trying to understand polarity. And those sorts of things are intriguing because they suggest all sorts of things about how the model is learning. And then whether or not there's an optimal starting point for the model, or whether or not it gets it requires the whole thing to work. So stepping back for a second, I mentioned before that we have these large language models that are trained somewhere else, hopefully, and that they provide you with the baseline. So in the context of probably the most well-known model, which is the BERT model, you have this bidirectional transformer, and the model is trained on hundreds of gigabytes of text, all of which are on this particular task. So the first task that we model is this language model modeling task that I mentioned before, where we have to predict the word in the sentence. And it doesn't have to be the last word. In fact, sometimes it's more interesting sometimes if it's the middle word. And what we have to do is train the model. So what we do is 15% of the tokens in our training data we will conceal, and then 10% of those tokens we will add a random word, and 10% of the time we will add the original word. And the reason to do that is to do with preventing the model from overfitting or preventing the model suffering from other problems. But then the word itself has to be predicted from it. So in this case, we would hope that the model would say, attention is all you need. And by doing that, it's able to identify those things. To allow the model to look at a slightly larger level, then we also have it identify the second kind of task. In this case, we need to say whether or not the second sentence is related to the first one. So in this case, they obviously don't, because what we have here is a quote, and then we have a statement about the United States, and obviously they don't follow from each other, but the model, it should be able to predict that, should be able to say these two things don't meet. You'll notice that there are these special tokens, and those are part of the way that BERT looks at the overall message that it's information that it's given. It's given these separated classes, or separated, sentences. Second thing that's interesting is that we don't just look at individual words anymore. And one of the ways that we can overcome a typical challenge with the original approaches to NLP is that we can now split words into subword units. And that allows us to avoid having to deal with unknown tokens in the same way. And so I took this sentence, I can't install Revit 2019, and you can see that the model sees I can, the apostrophe and T install, and then it splits our product Revit's name into two pieces. One is Rev, and then is a subword token as a postfix. So that allows the model to look at a fixed width up to 5, in BERT's case, up to 512 of these tokens, and model across the whole thing. So you have this large fixed window, but it is still actually technically a fixed window. So what does it mean to use a transformer? So in the classical way, classical machine learning, you would start from scratch. You would find a data set, you would begin to train it, you would then set your objective and go from there. In a transformer, we go in quite a different way. So what we first do is that we have this multi-objective self-supervised phase where the model has kind of explored the language space and understood the language model. And actually what can be nice about this is that you generally don't have to train that yourself. Retraining some of these models can cost between tens of thousands and millions of dollars, depending on the size of the model and the data available. And often even just acquiring the data in a coherent way can be difficult. So what's attractive about this is that our colleagues in other companies have published those models and made them widely available. And in doing so, that makes it very easy for you to get that model together. So in particular, we can take the example of the Hugging Face Transformers model, which a Transformers library, which is a Python library that builds on either TensorFlow 2 or PyTorch, and allows you to obtain a model very quickly and use it very quickly. So just to give you the example code here we have a model that is used for doing review sentiment analysis and can be done and is fully ready to go if you download it today. So the first couple of lines, you just create your tokenizer, as I mentioned, to develop your subwords. You load your model, and then you just, it's a very conventional set of encoding the model using the tokenizer, and then just pulling the outputs, the weights back from the model using a conventional kind of PyTorch language. So the nice thing about this is that it's very straightforward. This is not a especially complicated piece of work to do. You can see that once you have your tokens and you add your special tokens here, you pad the length to make sure it's fixed. And then the attention mask is to tell the model which parts are padded or not. And then all that happens is you get back your highest argmax, and that will give you the label. And you can then translate that back into whichever label it maps to. So, you know, as a piece of work, there you go. There's a complete sentiment analysis tool for review analysis. But obviously, there's a problem here, which is that this isn't my model. This isn't my information. This is someone else's multilingual uncased sentiment, and I would like to be able to do better. Oh, I should also mention that this model has been trained on multiple languages concurrently. So there are 6 different languages here that it will train to, it will recognize to a greater or lesser extent. So what I can do instead is that I can, I can do 2 things. Sorry. I can do 2 things. One is that I can customize the language. So as we saw, Revit, Autodesk has a lot of technical language. It has a lot of complex terminology. It has a lot of things that are probably not used in the same way as in general language. So what we can also do is take that original language model and continue to train it on a new corpus for more self-supervision on our own terminology. And this can improve the performance. It can help you with unusual constructions, and it can help you with terminological features. So you can do that, and you may only need to do that once. And then in addition to that, you can do this, which is to fine tune the model on your particular task. So if we want to do more text classification, or we want to change from a 5-star review model to some other approach, then it's very easy to do this. You just attach your head, you do supervised conventional training, and you need much less data than you did before, because actually the model has learned a lot from what it's seen before. And it can use that information. It's seen that huge base of knowledge in the core language model to do task-based stuff. So we spend a lot of our time building new models on top of our own language model and training it to particular tasks, training it to particular degrees. And so for this example, in a quick way to do it, you can train BERT on SageMaker. You can build yourself a very quick example using this run glue example, which is the best known kind of text classification system. And if you use the sort of SageMaker work that Alexander talked about in his last talk, it's very easy to put all of this information onto S3, and then you have on-demand training where you only have to use the GPU-based server for the amount of time that actually takes to train. So if it takes you an hour to train the model or 2 hours to train the model, you only pay for that amount of time, which is a great advantage when you might need 4 or 8 GPUs to get really good, to get the kind of consistent training performance that you want. I tried to provide another example to give people. So this is extremely minimal text generation piece of code. So this is a complete example. So you can see here, same thing. Now we have a different task with a different head, so GPT-2, OpenAI's model. And just to go through this in a bit more detail, you can see that line 13, we load the tokenizer from the pre-trained model. And actually, just by doing this, Hugging Face will go to its model repository, retrieve the configuration files and the binary files for that particular tokenizer and the vocabulary files, and download it and set it up for you. Same thing with the model. That's 500 megs. It just comes straight down. We use a prompt here. I use the extremely imaginative, hello, my name is Alex and I am. And all I do is encode that as before. So encode it, add the special tokens, come back as a PyTorch tensor, and then ask the model to generate from the prompt. And then I just print the result out as a decoded by the tokenizer. So the last layers weights come back out. And what's nice about this is that when I did this earlier, it said, hello, my name is Alex and I am a programmer. So I was extremely pleased at how high quality my results were. And as everyone knows, because it worked once, it'll work always. No, more seriously, it was nice to be able to see that these sorts of short pieces of work allow you to experiment very quickly with the code and get access to an enormous amount of previous people's work very rapidly and easily. One issue that does arise in practice when you come along to inference with these large models is that they do typically need GPU infrastructure for them to be hosted, and that can be very expensive depending on your traffic requirements and on how bursty things are. So we have a lot of applications where we have a relatively small number of requests per hour, but we have or per user, but we have large numbers of requests over the course of a day. And so there are two options that are of interest there. One is that you can distill models, so you can reduce the model size by up to 40%, because these huge models actually know a lot more than they need to. They have a lot more, they contain multiple examples of very good optimal submodules, so it's easily possible to either distill those models or indeed prune them down to the smaller sizes. The alternative option is that you can reduce the resolution. You can change from a 32-bit to a 16-bit float, and in doing so, or even down to 8-bit in some cases, and in doing so, you reduce the memory footprint of the model enormously and improve the performance. And so between distillation and quantization, it's entirely possible to place these highly advanced transformer models, these originally huge models, onto mobile devices or onto relatively low-powered devices quite easily. So where is this going? What's interesting about this is that we have seen this continuous growth in the performance of the different transformer models on specific tasks. Now, these fixed tasks obviously have the challenge associated with them that they do represent fixed challenges, so they're not really real-world examples, and real-world data is always messier, and the real-world environment is always messier. But there has been this relatively smooth progress in the performance of models based on the amount of compute and the size of the models that we've been giving them. And what's impressive about that is that suggests that these transformer models, which have these small fundamental operators that just scale up, so these kind of attention layers upon attention layers go on and on forever. Maybe not forever, but it suggests that we have more to learn and more space to learn in getting better performance from less supervised data and less provided data over time and along the way. And so the most recent GPT-3 model from OpenAI suggests, albeit with some methodological issues, that there is a real opportunity to keep scaling these models into the future. And that's quite exciting, because even if we do hit a wall eventually in those kind of scaling returns, we can then return to improving the complexity of the models and trying other things out to get even further down the path. So I think it's still an exciting time to be in natural language processing, and especially in the fact that this stuff becomes very immediately relevant to industry and very available to industry, which means we can rapidly apply it, and that gives real world experience back to everyone. So if you want to have a look at how a BERT model works, you can take advantage of the Expert project, which I think is very interesting, because it shows you this kind of situation where you have these multiple attention heads all looking at the different weights of the words. And along the way, you can then explore how the different model weights go. These kinds of things provide you with plausible insight into the way the model works, but they are not definitive explanatory functions. So there's this challenge along the way that you need to be cautious about how many conclusions you draw from the way your input weights affect the subsequent layers. I've cited a couple of papers at the end here, which you can begin to read to decide how much you trust attention-based explanations, but at the very least, it allows you to kind of begin to get a feeling for comparative performance of the models. Another thing I want to make bring people's attention to or mention to people is that these are pre-trained models. So they are pre-trained on a corpus of text that they have seen. And so the model learns both to distinguish things, but it has no inherent sense about what is a positive or a negative bias in the data that it sees. Moreover, algorithms themselves can display all sorts of bias. So even if your data was relatively neutral, you can still run into a lot of challenges. And this is a sort of a simple example to illustrate the challenge that we have here, which is that I've asked a BERT model to predict the difference between whether it thinks a doctor is more likely to have a male or female pronoun and vice versa for a nurse. And you can see that there is this tendency for the models to strongly prefer one over the other. And this is not to say that these technologies can't be used, but they should be very carefully thought about, especially anywhere you're going to make any sort of impactful decisions for people on, that you make sure that it's possible to understand whether or not your workflow is resilient to unexpected or unintended effects from the way the model has been trained. So wrapping up, I do want to mention one other thing that's a big challenge, and I would encourage people to have a look at this thread. One of the big challenges in commercial natural language processing is that people have a relatively narrow sense, I think, sometimes of what the possible tasks are. I've talked about a whole variety of them here, but actually people tend to think in terms of sentiment analysis, and they tend to think in terms of news classification. And I think there's a lot more out there to be done, and it's actually possible to learn. If you can learn how to translate these problems into relevant tasks in the models, it is easy to an unprecedented degree to get high performance from that using approaches like this. So I would strongly recommend that if you are interested in this area, it's a good time to get into it. And it's an opportunity for a lot of companies who are now thinking about any text they get from their customers as an opportunity for automation. So just to conclude very briefly, we have these transformers that build on a huge amount of learning that they've had trained by other people, large corpuses of text that have been selected from outside. You attach a head, you build this task-specific environment, you may optionally fine-tune it. But what's important about it is you get this immediate leg up, you get this tremendous speed increase in your work so that you're not starting from zero when you develop the project. And in the end, you should get pretty good performance, certainly, if not gold, at least bronze. Thank you very much. And here are some of the citations and some of the other links that might be worth looking at if you're interested. And those are some links. Cool.
Cool, that's great, Alex.
Very cool, thank you.
Great talk.
Awesome.
Okay. So I see there's a few questions in there actually. So Stephen McInerney, Alex, can you say more about the pitfalls and weights in attention-based models?
Yeah, so I think that there are a couple of pitfalls to think about. One is that it's important to make sure that the training that you do and the way in which you select your baseline model is actually well aligned with the task that you have. I think also, if you do have highly specific language, then you can sometimes run into some challenges with the way the models have to learn new concepts along the way. So there's a lot of fine tuning to be done there too. And then thirdly, these are off-the-shelf models trained in a noisy fashion. So all of the challenges of that very simple example of bias I mentioned are actually like encoded both in the general kind of societal bias, but also in just linguistic bias that may not help you on your task.
Great. Yeah, there's a couple of other questions there from Sumia as well, Alex. Great talk. The translation from Word to Vec neural net onto transformer type architecture has been massive. What's your opinion on further research advances in this area, perhaps 5 years from now?
If I could tell what was going to happen in 5 years, I'd be a very wealthy man. But I think that there are kind of three directions that are interesting. One is continuing to make even more giant models. But we have this interesting issue there, which is that who has the money right now to spend $5 million to train a single model? There are not a tremendous number of people out there who can do that, especially for risk. So at the same time, there are other places that we're doing that are interesting work is being done that I would highlight. One is in areas of like the reformer and the related locally sensitive hashing transformers. So the idea here is instead of taking that raw sequence of subwords, I apply a hashing function to it, and that allows me to have a very large input. So I can now input 10,000 words instead of 500. So learning over a whole novel, inferring over a whole novel is a fascinating kind of concept, and I think something that's intriguing from that perspective. The other thing that I would mention is that there are other aspects that applications where the models don't yet perform well enough that are intriguing. So to plug my own work with Adapt, one of the things that we're very interested in is where you have an intermediate representation, where you have some structured text that you want to generate text around, how do you help with the model otherwise hallucinating or otherwise failing to produce the text that is true to what the facts of the world are? So all of that questioning around how you would actually go from this kind of free association of text that a default language model does to something that's descriptive and grounded is also interesting.
Okay, and then another question from Sumia was, do you see a gap between academic papers versus industry implementation in this area?
I think there's been a smaller gap than ever before in that. I think that there is wider participation by academia in industry and vice versa. It's not perfect, but it is better than it used to be, and I'm hopeful of even better in the future.
Okay, and I have one more question from Alex from Morehouse. Thanks, Alex. If these models can generate human-level quality text, do you think this will pose risks on reality and facts mainly, and how can we minimize those risks in your opinion?
So there's been very interesting work on trying to automatically detect automatically generated language, if that makes sense. And the Glitter project is one of those that I would mention. And what's, so far we are in the same situation as we are for forensic analysis of images, which is that you can look at the mathematics of the generated text and make a pretty good judgment as to whether or not a model did it, because it follows a kind of a lower probabilistic manifold than a human generated text. So I think for now we have a little bit of space ahead of us in terms of that sort of thing. In general, I think it also maps to the situation of our experience with video and image, which is that yes, things like Photoshop, yes, things like deep fakes have created worries, but honestly you can reproduce a lot of the same effect with manual authoring, and we have to be just as worried about camera lens angles and those sorts of things as we do about automation. So maybe it'll happen at more scale, or maybe we'll be able, this is a relatively easy thing to find compared to truly deceptive content.
Okay, and one final question, another one from Stephen McNary. Sorry. So what place do you still see for Word2Vec, and what size data set do you break over from Word2Vec to Transformer? Are collections and forward context still an Achilles heel to Word2Vec?
So I haven't done any specific work on the kind of size of data changeover, but actually, funnily enough, I think often you need less data for a transformer-based approach than you do a Word2Vec-based approach. The other place that's it's useful is the other thing that you can do is you can get some of the transformer architectures to emit a stable embedding the same way that Word2Vec does. So you can use it as a drop-in replacement, and we have some projects where we use a different set of transformers to actually do that. So I think it would, if you are using Word2Vec right now, and especially if you're using Word2Vec where you're doing summing the vectors or averaging the vectors over a sentence, I would say that it might be worth your while just trying to drop in another transformer-based approach and see if that gives you improved performance.
Great, thank you. Okay.
Thank you.
So yeah, thanks a million to all of our presenters. They're really fascinating talks and ones that actually would not have been possible in the same way in person. So it was really great to have them and to be able to share them in this way. Yeah, so hopefully we'll be able to do this again soon, guys, and have even same quality of presenters again. It'd be brilliant. So I guess I'll sign off, and if there's any volunteers or people who would like to suggest topics or focus areas for upcoming talks, please, as I said at the outset, feel free to get in contact with any of the hosts on the meetup site. Just drop us a note.
Thank you, Claire, for your great emceeing.
Thank
Thank you
you.
very much, Claire. Thank you, everyone.
Thanks, everyone.
Thanks. Bye.
Thank you. Thanks.